Okay, welcome to Chem 1311. Hopefully you guys can hear me if you're in the back. So my name is Tom Tietz. I'll be the instructor for this section. And it might be a little bit crowded today. It looks like there's some empty seats. I think they made the class capacity the size of the room, but don't worry, in a couple weeks that'll be better, so it won't be so crowded. All right, so what I have here first, just something that's going to happen from time to time and happen to fall on the first day. I will occasionally let you know and advertise certain things around campus that people ask me to show to you guys. So this one is about learning abroad. So if you want to go to another country for part of your education, there's opportunities to do that. And so the information will be in the notes when they're posted on Blackboard later today. So you can definitely check that out if you're interested. All right, so the goal for today is to go a little bit over an introduction to the course, and then I will go into the very first material that we're going to cover in chapter 1 of our textbook. So usually when I teach this class, I'll spend at least about half of the first class going through things on the syllabus and giving various motivational speeches and things, but that often results in us getting a little bit behind at the beginning. So I'm only going to do like a couple of slides, maybe 5-10 minutes on just a general background about how the course is organized. Most of it you'll figure out as you go along, and there's a lot of documents and things in Blackboard that you're encouraged to read and look over to help you understand. But for the most part, this course follows a pretty stable, pretty steady routine throughout the semester, so it's not too hard to figure out everything you need to know. All right, so here are some of the important things. So this one I wanted to bring up because there is a bit of a time-sensitive component to it, and that's your textbook. This class is part of a pretty new university program called CTAP, which I think stands for Cougar Textbook Access Program. If there's a C, of course it means Cougar, but I think that's the rest. And so CTAP basically gives you guys all access to the ebook through Blackboard. It does require, I think it's about a $35 fee for the whole semester. So it's basically a rental fee, and it's an ebook that you have access to. So by default, you all have access to that. And it is encouraged that you have access to the textbook in some form. But if you have another copy of the book already through other legal or illegal means, I'm not going to ask, but if you have another copy of the textbook and don't want to use the one through Blackboard, you can opt out of it, but you do have to take a step to opt out. And the instructions for that are in Blackboard. So if you don't want the textbook through CTAP, make sure you opt out. I think usually about 90% of students participate through CTAP, so it's pretty widespread and it's pretty useful because it does give you the book for a lot cheaper than you can get it from the bookstore. But nonetheless, if you want to opt out, you have to do that. All right, so the first thing on our plate in terms of assignments are going to be homework assignments, because they do occur every week, and the first one is due at the end of this week. So they're always going to be due Sunday at 11:59 p.m., so basically the close of the day Sunday is when every homework assignment will be due, and we'll have one per week. We'll skip a week for spring break, but other than that, there's going to be one per week. So the first one is due this coming Sunday, and it covers what's called the review chapter in your book. So that's the only part of the book that we expect you to sort of self-study or go over on your own. That won't be covered in a lecture. I did post some notes and a video on Blackboard for that chapter if you want to use that to help you. But the assignment that's associated with that is due this Sunday. And the way the homework works is you get 4 attempts per week. So every weekly assignment, you're allowed to do it 4 times, and we only count your highest score towards your grade. So there's no disadvantage of doing it all 4 times. And in fact, it is strongly encouraged that you do that every week. I have some statistics in a file in Blackboard that you can read that show that the students that do all 4 homework attempts per week perform much better in the course. So if you want to pass the course, get a B, or a C in particular, then doing all 4 homework attempts per week is sort of the minimum of your effort and something that you all should be doing. The way that we calculate your final homework average, so it's, as you'll see later, it's worth 6% of your grade, but we do drop your 2 lowest homework scores for the semester. So out of those 14, your top 12 will actually count towards your final grade at the very end. And as I already wrote once and now said here again, the homework assignment will open up at 12 a.m. on Sunday, and then the following Sunday at 11:59 is due. So it's basically open for 8 days. And what that also means is if you wait until Sunday to do your homework, which an unfortunate percentage of you will do, if you do that, then there's going to be 2 homework assignments available on Sunday. The one that just opened up that's not due till the following week, and the one that's due that night. So you have to make sure you do the correct one. Some of them have similar names, especially if there's 2 assignments from the same chapter. So look closely at the due dates. Those are all clearly posted in Blackboard. And if you're going to do a homework at the last minute, make sure you're doing the correct one and not the one that just opened. All right. So the exams, which we don't have to worry about for a few weeks, but just to give you some information about them, those are taken in CASA. And CASA, if you haven't been there, it has roughly the popularity of the DMV. It's not a great place, but that's how we do them. So you take the exams in CASA, and we will use Blackboard for the exams as well. They're all electronic. So we're going to have 3 midterm exams spaced pretty evenly through the course. So the first one is pretty much exactly a month from now in February. And then they're going to go every 3 or 4 weeks after that. So the midterm exams are 20 questions each, and you have 75 minutes. And then there's going to be a cumulative final exam taken right during the pretty close to the beginning of the final exam period. Ours is usually pretty early, and that's 34 questions and 100 minutes. And again, there's details about the schedule and the syllabus in Blackboard, so you can certainly check that out. And then once we have all of that at the very end, the grading is pretty straightforward for this course. So each exam question is essentially worth 1% of your grade, because the midterm exams are 20 questions and they're worth 20 points each. So in total, that's 60 points out of the 100 that you'll get. The final exam is worth 34. As we said, the homework is going to be count towards 6% of your grade, so that adds up to 100, 60, 34, and 6. There is the opportunity for 2 percentage points of bonus throughout the semester. Again, details on how I determine your bonus points are in a document in Blackboard. It's called what is it called? Section-specific information. It's like a syllabus supplement just for this section, because the bonus points are different for every section of this course. They're not every instructor does it the same. Everything else is the same. The way that I do bonus is determined by the number of homework attempts that you do. As I said, that's one of the key predictors of success in this course. So to encourage you to do all 4 homework attempts every week, that's how I'm going to determine how many bonus points you get. So if you do all 4 homework attempts every week, you'll get 2 percentage bonus points. If you do 0 homework attempts per week, well, you'll get 0 bonus points and you'll fail the class, so both of those things will happen. And then if you do anything in between, your score is going to be basically determined by how many of those homework attempts that you do. So basically it's 0.5 per attempt per week, and then we average it all out at the end. So it's only 2% total on your final grade, not 2% per week, but it's going to be determined by those homework attempts. So make sure you understand how that works. But if you're doing all the homework attempts like I've asked, then you have nothing to worry about there. Here's our grading scale. I get asked a lot, especially at the end of the semester, do you guys curve? I guess not really. We do make the scale a little bit easier than the standard UH scale. So you'll notice here that our A goes down to 90, our B plus goes down to 80. To get a C minus, you need a 60, and so it's a little, it's an easier grading scale than what the standard is for UH. But we don't typically change that, and we don't curve you guys against each other. So if everybody in this room gets a final average above 90, everybody will get an A. We're not going to rank you guys or do any sort of curving down or anything like that. So it's the only competition you have is between yourself and the grading scale, not with each other. So keep that in mind, but we don't typically change it either. We never have. I've been teaching this course for, I don't know, this is like my 8th or 9th time teaching it over the last 8 years, and we don't change the grading scale, at least we haven't in the time that I've been here. So this is what you can expect it to be, and that's what you're going to shoot for depending on what grade you want to get. All right, so that's that. You are welcome to interrupt with any questions as we go through this. Don't be shy, but as I said, a lot of this stuff is in Blackboard. So here's some information specific about my class. All right, so my office is in Circ 5023, so we're basically right here at the moment, and so you just have to walk to the end of this building, and that's the one you run into is Circ. There's a little walkway between them to guide your path, and then I'm on the 5th floor of that. So that's where my office will be located. My standard office hours are going to be immediately after class on Tuesday and Thursday, so 11:30 a.m. to 12:30 p.m. I guess I'll remind you now because, so on this Thursday, which is the 19th, there's not going to be office hours. So once in a while, not very often, I'll have to cancel I try not to schedule things on top of office hours, but that doesn't always happen. So no office hours this Thursday, but in any other week, you can count on it being Tuesday and Thursday, unless I let you know otherwise. Those are the times that I encourage you to come if you're able to. If those times don't work for you, please don't hesitate to contact me. If we can work out other arrangements if you want to come see me in person, or we can do questions over email, virtual meetings. I'll be pretty flexible with that because I know not all of you are going to be able to come during these times that want to, but that's the time that I'll definitely be in my office, and again, with rare exceptions, will be available. I'm also usually pretty flexible in the afternoon hours on these days, so as long as you get there by 12:30, I'll usually be able to stay around until you answer your questions and not have to bail on you right at 12:30 either. So keep that in mind also. Just get there by 12:30 and I'll make sure I'm there. And again, I'll remind you of updates in class and also post them on Blackboard when necessary. The best way to contact me is email. If I'm in my office, which is not all the time, you can call the office phone number and I'll answer. But for obvious reasons, I won't give you my cell phone number, sorry. So you're gonna have to mainly email or hope that I'm in my office if you wanna call. And again, there's a document in Blackboard that has more information specific to this section. Doesn't really affect how we grade the course, or all the assignments are the same, but different things that are related to this section. Now, another thing about office hours, as this little graphic kind of indicates, there's always an assumption. I used to teach sections that were like 500 students. Now we're a little bit more manageable at about 216. There's always the assumption that, there's so many students in the class, no, he's not gonna have time to talk to me, or there's gonna be a lot of people there. For whatever reason, students don't usually come to office hours, so it's not usually that crowded, so don't let that deter you from coming. And like I said, I'll try my best to accommodate everyone. We have some bigger rooms on my floor that we can move to if there's a big group of you guys all at the same time. My office isn't huge, but there's other rooms available usually, so we'll work it out, so don't be deterred from coming just because of that. All right, I think that's all I had on just the course organization, the syllabus. Like I said, you'll need to read it yourself and become more familiar. Any questions on that before I move on? Yeah.
For the calculator requirement, is a TI-84 acceptable, or?
I believe not. Is a TI-84 a graphing calculator?
Yes.
Yeah, so no graphing calculators are allowed on exams. Obviously, I can't police what you guys use on homework assignments, but you want to get used to using the one that you're going to use for an exam. It has to be a scientific calculator. No memory function, no graphing functions allowed. So that if you want to stick with the TI series, the TI 30 somethings, whatever of those you can find are usually really good. But any scientific calculator is perfectly fine. And again, that's CASA that's going to check that. So I can usually, if you're unsure, I can tell you, this calculator is fine or this one's not, but it is going to be CASA that enforces that. So just make sure you don't show up with a graphing calculator. I think the computers that you use in CASA have also a calculator on the computer for simple functions. So I'm not sure about that, though. Don't quote me on that. But anyway, it has to be scientific. Anything else? All right. So we will move on now and actually start the course. I know usually you appreciate the nice syllabus day, but we're going to just have like a syllabus 15 minutes today. And the first thing I want to cover is the scientific method. Now, this is more directly relevant to the lab course where you're actually going to be carrying out the scientific method, but it's important to appreciate in here as well because everything that we learn in this class, everything that was discovered sometimes hundreds of years ago or sometimes more recently, depending on the topic, all of that came about because of people applying the scientific method and using that to learn something about chemistry and understand a physical or natural process. So there's sort of three steps to the scientific method. So the first is an observation. So as a simple definition, this is something that you sense or measure. And there's sort of two types of observations, qualitative and quantitative. We want to understand a little bit about the difference between those. And both can be useful in different situations, so it's not to say one is better than the other. A qualitative observation is one that is not measurable in a absolute sense. So it'd be something like, the sky is blue today, or Professor Teets has curly hair. Both of those are observations, but they don't tell you anything really specific or measurable. Whereas a quantitative observation is one that has a number and a unit associated with it. So you would say that that car is traveling 60 miles per hour. That's a quantitative observation about how fast the car is going. Or Professor Tietz is 5 feet 9 inches tall. That's a quantitative observation about something. So it always has a number and a unit associated with it. Now, once you have an observation, so the scientific method starts with an observation. You see something, you measure something, and you want to try to explain what's going on. Then you formulate what's called a hypothesis. Now, a hypothesis is a possible explanation for what you observe. So you want to explain what you observe, and the hypothesis is sort of your first guess at that. So it's a possible explanation, and it's usually based on limited or flawed information, because a single observation, or even a small set of observations that you've made, is not usually enough to really understand what's going on. But it's not a total wild guess either. Some people think a hypothesis is just a wild guess. But we have a lot of, especially when we're doing science, for real at the level that you guys will be doing it in your lab especially, we have background information. We have, knowledge that's already built up that we use as part of our hypothesis. We're not just throwing things out, out of nowhere. So a hypothesis is an explanation for that. And usually it's based on flawed or limited information. So it's not usually correct, but it's something that you can test. And the way that you test your hypothesis is with an experiment. So you design experiments to carefully test the hypothesis. You say, well, if this hypothesis is true, this is what should happen in this experiment. And you observe whether that does or does not happen. And if it does happen, that is possible confirmation that your hypothesis is right. If your experiment doesn't match the hypothesis, then you have to refine the hypothesis. So basically, you repeat this cycle over and over again, because every experiment is going to generate a new set of observations, and then you evaluate whether those observations fit the hypothesis or not, and then if they don't fit, you have to modify the hypothesis and test it further, and that process just goes on and on and on until we feel pretty comfortable with what we're seeing and how we're explaining it. So once you've applied the scientific method over and over again on a certain topic, once you've studied a system many, many times, that leads to two things, and both of these we're going to talk about in this class. So one is a law, and at a very simple level, the law is what happens. So it's a repeatable set of observations. So we're going to talk about some of them today, but a law, for example, that you may have heard of in your other courses is the law of gravity. If you drop something, it will fall to the earth, and it will do so with an acceleration of 9.8 meters per second squared, and so on. So that's the law that describes, what is happening. It can be quantitative, it can be qualitative, it can be both in many cases, but it describes what is happening and what is a generalizable observation. And then what you also develop in the course of doing the scientific method is a theory, which is an explanation for why it happens. So the theory is sort of related to a hypothesis, but it's a hypothesis that's been, so thoroughly tested that we accept it to be true. Now, some theories end up being flawed or wrong. So the way the scientific method works is you have a theory, but then sometimes you find something that goes against that theory, which means the theory is not complete or has to be refined. That's the case. But the theory is sort of the explanation for why it happens. I think in the popular media, the word theory kind of gets used incorrectly a lot. The theory is not just some wild musing of a scientist of, I think this is happening. No, a theory is really an explanation based on a lot of observations, and it's often used in conjunction with laws to explain why it's happening. So we talked about the law of gravitation that you've probably all heard of. So the law of gravitation says how fast something will fall to the earth and so on, and then the theory would explain why that happens. And as it turns out, the theories behind gravity are still kind of up for debate right now, so they're not even really finalized themselves. But the theory would explain why that's happening, the law explains what is happening, and those two always kind of go together in scientific method. So we're going to talk about that today, actually, is going to be the major topic, are three of the early laws of chemistry that scientists discovered, and then the theory that kind of explains all of those and brings them together. So we'll see both of those aspects today in what we cover. All right, now the topic of this course obviously is chemistry. So the scientific method can be applied to pretty much anything in the world, any physical observable phenomenon you can use the scientific method. We are specifically concerned with chemistry in this course, obviously. So let's break down a little bit of what chemistry is. So again, we use the scientific method in chemistry. It's not that these are two separate things, but what are we studying in chemistry? So at a very simple level, chemistry is the study of matter. And matter is the stuff that makes up everything in the world. So whether you're talking about the air that you breathe, the water that you drink, the desk that you're sitting up are made up of different kinds of matter. I mean, it's really a study of everything that composes this entire world. Within matter as a whole, there are two major classifications, and we're going to talk about both of these in this class, although the second one that I'll give you is one that we're going to talk about more often. So matter can be either a mixture, which is variable composition. In our everyday life, we encounter mixtures all the time. Pretty much every beverage you drink, unless it's pure water, is a mixture. Most of the food you eat is a mixture as well. I would say all of it. I can't think of any pure substances that you eat, but maybe there are some. So anyway, mixtures, they have variable composition, meaning they're more than one thing mixed together, and the amounts of those things can vary depending on how it's prepared or how it's formed. And then the one that we're going to talk about the most in this course, we'll get a little bit to mixtures at the end, and especially if you take Chem 2, you'll see a lot more about them. So it's not that we completely ignore it, we just don't get to it in this class so much. But the one that we do talk about a lot are pure substances. So these are materials that have constant composition. So if you have we'll talk about this in more detail, but if you have a pure substance, no matter how you prepare it, no matter where you get it from, the composition of that substance will be identical. And that's what we mean by a pure substance. It's not mixed with anything else. It's one thing by itself. And then within each of these, there are also subcategories. As I said, mixtures are not going to be a major part of this course, but I'm just going to introduce it here for completeness. So mixtures, we have two kinds, homogeneous and heterogeneous. I'm not even sure if this terminology will come up on your homework assignment or not, but it could be there, so be aware. So homogeneous and heterogeneous. Homogeneous means a single phase, which essentially means you have a mixture, but you can't easily tell by looking at it that it is a mixture. Classic example of a homogeneous mixture is salt water. So if you take salt and dissolve it in water, it still pretty much looks like water. You can't tell that there's salt in there. There's other things you can observe to tell there's salt in there, but you can't tell just by looking at it. So we call it homogeneous. Whereas heterogeneous is one that has visibly distinguished parts. One of these days I'll learn how to spell visibly distinguishable parts. So a heterogeneous mixture, there's a lot of those out there as well. Maybe an easy one is that you've probably seen is, sorry?
Salad.
Salad would be a good one, yeah. So you have multiple components, unless you're eating a pure kale salad or something. But yeah, if you have multiple components in the salad. Sand, if you go to the beach, especially if you look at it under a microscope, you'll see that there's a lot of different things in there. So that's a heterogeneous mixture where you can tell just by simple observation that there's more than one thing in there. Within pure substances, there are also two major categories that we'll talk about. And as I said, this is the bigger emphasis in this course. So there are elements and compounds. So don't worry too much now about the precise definitions of these, because that's all coming. But at the moment, we can say that an element is a substance that can't be broken down further. So if you do any sort of chemical or any physical treatment of that substance, I should say. So if you heat it up or try to decompose it, it's not going to change its composition. Whereas a compound is a combination of elements, so it has more than one element in it. So it's a combination of elements. And if you break down a compound, you can then get the individual elements out in many cases. And the whole study of chemistry is really how we convert between these. So chemical reactions or chemical methods allow us to combine elements into compounds or to break elements down to break compounds down into their elements. For those of you that came and are on the floor, there are some seats in the back right where I'm standing. So if you want to make your way over there, there's some empty seats here and there. Not on this side of the room though. All right, but that's what the study of chemistry is. It's taking elements, converting them into compounds, taking compounds, breaking them down into elements, or taking compounds and converting them into new compounds by different chemical reactions. So that's going to be a major topic of this course, especially sort of the middle parts of this course. We'll talk a lot about chemical reactions. All right, so that's kind of a breakdown of what we're studying in chemistry. You don't need to know the specifics of all these right now because that's going to be everything that we pretty much cover in this course. Now, the other thing that we can do is look at the microscopic level to understand a little bit more about the classifications of pure substances and mixtures. So this feels a little bit out of place because we haven't talked about atoms and molecules yet, although we're getting there soon. But there might be some homework questions along this line, so we're going to introduce it at a very basic level. So as we said, an element can't be broken down further. And so as we will learn then in a little bit, an element is made up of one type of atom. So we're representing different atoms with different colors here. So hopefully we don't have too many colorblind people in the audience because that might affect your ability to understand this slide. But nonetheless, an element has one kind of atom. So they can be either individual atoms floating around, or as we'll learn, some elements exist as molecules, but those molecules have two of the same or more than two of the same atom bonded to each other. So it's still classified as an element because it only has one type of atom, even though two of them are joined together. Whereas in a compound, you have two or more different elements chemically joined together. So at the microscopic level, you would see two or more different atoms, but they are again joined together into what are called molecules, and those molecules sort of exist with a strong bond between the two. And you can have different ratios. So some compounds, as we showed here, will be very simple. One blue atom, one pink atom. Other times you have a more complicated composition, like one pink and four black. Whatever the case is, you can have different ratios of two or more different atoms bonded to each other, but that's what a compound is. But again, in both of these are both pure substances, as we said. So the element and the compound will both be classified as pure substances because there's only one type of microscopic particle that makes them up in each case. Whereas if we had a mixture, you can have a mixture of elements as we have here, or a mixture of compounds as we have over here, or you could have compounds mixed with elements. I don't have that possibility, but that's obviously there. We have, in this case, two different types of microscopic particles, atoms or molecules, that make up that substance. So in a mixture, you would have, in this case, red and blue mixed together, but they're not chemically joined. There's no bond between them. We're going to learn what chemical bonds are in about chapter 3 or so, chapter 4, around that time. But there's no bonds between these. They're just physically mixed together. Similarly, we have two different types of molecules in here, and the molecules have no real chemical interaction between them, but they're just physically mixed. So that's kind of a little bit about the microscopic level of how we would classify and distinguish elements, compounds, and mixtures. A big part of chemistry is sort of understanding the relationships between the microscopic atomic scale and the sort of macroscopic scale of what you see and what you observe. So this is kind of our first taste of that, although, as I said, a lot of the details are going to be fuzzy at this time because we haven't covered any of the topics. But there might be some sort of graphical questions like this in the homework assignment that ask you to think at a microscopic level how you would distinguish these different classifications of matter. So this gives you just a little bit of an introduction to that. All right. But now we're going to start moving into something a little bit more systematic and a little bit more logical, I think, in how we're going to present it, which is building up some of the earliest chemical foundations. So how did chemistry start? What were some of the first things that people learned? And how did that then lead to, further and further advanced developments that have defined now the field of chemistry as you know it today? So in the very early chemical history, there were sort of two groups of people that over a long time span were kind of the first to start investigating substances and trying to understand them and trying to make some sense of them. So the ancient Greeks were one of them. A lot of those famous Greek philosophers that you've probably heard of were also involved in sort of thinking about chemistry. Now they didn't really do the scientific method at this time. So the ancient Greeks were interested in chemistry and they thought about it a lot, but they didn't have really the concept of a scientific method for how to actually study it. But nonetheless, they actually came up with some pretty interesting ideas. So they tried to explain chemical changes. A lot of chemical changes you can observe, like metal rusting. If it's iron, it'll turn sort of to a red-orange color, or rusting copper. It's not really called rusting in that case, but copper turns green if it gets exposed to air. So these are things that substances that they would have worked with and studied over at that time, they could already observe with their own eyes, and they tried to explain it. Now, the Greeks' major proposal was that there are 4 fundamental substances. So they were earth, fire, air, and water. So this is very similar to Captain Planet. Does anybody know Captain Planet? Okay, one person. I always reveal how old I am when I say that. So it was a popular cartoon back in the day where they had earth, fire, wind, water, and heart, I believe it was. They were a little bit more advanced than the Greeks. But anyway, the Greeks had 4 fundamental substances that they proposed: earth, fire, air, and water. But what's really interesting about the Greeks, even though they knew nothing about this or had no real way of experimenting on it, they were the first to propose atoms as fundamental particles. So they were not able to do experiments at that time to prove this or test this, but they came up with the idea somehow that substances are made up of little tiny pieces called atoms. In fact, the word atom comes from a Greek word, atomos, which I think means something like tiny or something like that. But anyway, they were the first to propose atoms as fundamental particles, although, as I said, that was more of an educated guess than a real theory or anything that was testable at that time. Now, another group in earlier history that was very involved in building some of the foundations for chemistry are called alchemists. Now, alchemy is what you would classify as a pseudoscience. And it spanned around 2,000 years. So alchemy was a big thing for a long time of human history. Now, we call it a pseudoscience because they were doing experiments in some level. They were mixing substances together and observing what was happening and formulating some ideas about how to explain that. So there was some scientific experimentation going on, but it was all based on the flawed belief, and what they were trying to do was to change base metal, typically lead, into gold. So back then, and to some extent still today, wealth and power are motivating factors for a lot of people, and the more gold you have, the wealthier and the more powerful you are. So alchemists believe that you could find a way to take really cheap, really useless or worthless substances and turn them into gold. That was their whole idea. Now we know today that that's not really possible, and it's certainly not possible the way that they were trying to do it. So it was based on a flawed idea, so that's why I call it a pseudoscience. They were never going to achieve their goal that they were set out to do, but they still made some observations along the way and still kind of set the stage for what was to come next, which is the real advent of chemistry. So the very first chemist, or who's often sort of credited as being that, is Robert Boyle. And we're going to learn about some of Boyle's discoveries much later in the course, probably about 2/3 of the way through. But what he did was he made quantitative measurements on gases. So we talked about qualitative versus quantitative. A lot of the early chemical history was qualitative. It was, color changes and sort of physical observations based on just what you can see and sense pretty easily, smells, taste, stuff like that. But he actually made quantitative measurements, so really setting the stage for understanding how those work at a much more detailed level. And he was also one of the first to propose the concept of elements, the idea that there are some fundamental substances that cannot be broken down further, which we now know of as elements. So he's credited as being the first chemist. And another very important early figure is Joseph Priestley. So he's credited with the discovery of oxygen. And he's really the first person to do careful studies of chemical reactions. So Boyle did physical measurements on gases. He measured different properties of them that we'll learn about later and sort of quantified some of those, but he wasn't doing chemical reactions to change one gas into another. He was just measuring a gas, usually just probably the air in his case. Whereas Priestley was actually doing chemical reactions of changing one substance into another and beginning to understand how that works. And especially the idea of oxygen was important because one of the most common chemical reactions that you can do, especially in early history and that they were studying at the time, was combustion, burning something in air. And for a long time, nobody knew how that worked because when you burn something, obviously, as we know now, and we will learn later in this course, it involves oxygen from the air. But they didn't know that oxygen existed, and they couldn't really quite figure out, well, how is the substance changing like this? How is the mass changing if there's nothing else involved? And they figured out that there was, oxygen in the air. You can't see it. It's not easy to observe directly, but he figured out that it was there, and that helped people really better understand a lot of chemical reactions that involve oxygen. So those are some of the early people, the groups and the individuals that led to the start of chemistry. And in the early history of chemistry, which I don't remember the exact years, but was something on the order of 200 years ago or so, people came up with three important laws. So as you said, a law is based on a series of experiments, observations that allow you to formulate a definitive statement of what happens. And the first one we're going to talk about is mass conservation. So I have a video here, but I did not queue it up, so let me do that real quick. Oh, exit full screen. I guess it's not treating this as a link. Oh, come on. Maybe next time I'll be prepared. This is going to be all messed up. I should have gotten this ready beforehand. Sorry about that. Once in a while I'll show videos in class. Hopefully this one still works. All right, so this is going to be a demonstration of conservation of mass. And of course there's an ad. Come on. Do we really need an ad on this? By the way, there are ads on my YouTube videos and I don't get paid for them, so I don't know why that happens. But okay, so anyway, he has two substances here. Both look like clear liquids, colorless liquids. And what he's going to do, or he or she, I can't tell, but the wedding ring looks male. I think I missed a second, so let me go back to the beginning, sorry. Okay, so he starts by looking at the mass, which is 158.2, is actually stated here at the top. And then allowing the two liquids to mix together after some deliberation. Okay, so there we go. Liquids mix together. Clearly something happened. You get this cloudy yellow substance all of a sudden. So a chemical reaction occurred. And we'll learn later on that's called a precipitate. So when he puts this back on the balance, it is still 158.2 grams. So even though there was an obvious chemical change, something clearly happened there, the mass was the same before and after that chemical reaction occurred. And so that's what we refer to as mass conservation, or the law of mass conservation. Okay, so that's mass conservation. And the person credited with this discovery is Antoine Lavoisier, who, as you might guess, is French. And so what it states, as we kind of already observed, is that if you have a chemical reaction, the total mass of what you start with in the reaction which we will call the reactants in a chemical reaction. Again, we're going to get into chemical reactions a lot more in a few chapters, but the things that you start with in a chemical reaction are called the reactants. So the two individual colorless solutions that the guy had in the video are called reactants. And that mass will be equal to what forms during the reaction. So he formed that yellow substance, and also a bunch of liquid as well was still present. but at the end of the reaction, the mass was the same. So the mass of the reactants is equal to the mass of what forms, which we call the products of the reaction. All right. And another way to state the law of mass conservation is that matter is neither created nor destroyed during a chemical reaction. That's probably the most straightforward of the mass laws, and we've probably heard of it in some context before. Matter is neither created or destroyed. If you do a chemical reaction, mass of reactants equals the mass of whatever products you get. So I don't think there's much more we need to say about that one. Now the next mass law that we want to cover, though, is called the law of definite proportion. And this one's a little bit more complicated, but not too bad to understand. And the person credited with it is Joseph Proust or Proust. I believe it can be pronounced either way. People ask a lot of times, do we need to know all these names? You should probably be at least familiar with the names I put in the notes. That it's not a major emphasis of our assignments or tests. I'm not, but there's a chance that there could be a question here and there that asks you to know some of these names. So appreciating history is somewhat important. So we ask you at least the basics. Okay, so the law of definite composition deals with compounds. We said compounds are substances that are made up of two or more different elements chemically combined together. So that's what the law of definite proportion concerns itself with. So a given compound always contains the same proportion of elements by mass. Regardless of the source. So if I take some sodium chloride salt, table salt as it's commonly called, and if I buy some of that at the grocery store, it's going to have some percentage of sodium and some percentage of chlorine in it. And then if I mine salt on the other side of the world, I think the biggest salt mine in the world is in Pakistan, but I could be wrong about that. But anyway, if you go to the other side of the world and mine salt there, and then you compare that's going to have the exact same proportion of sodium and chlorine. So it doesn't matter where you get that substance from, the ratio of the elements in that substance are always the same, and that identifies that specific substance. So here's sort of a numerical example to help you understand this. And these numbers will make more sense later on. But if we had 44 grams of carbon dioxide, so carbon dioxide is a gas that you exhale when you breathe, and it gets a lot of publicity because of its potential environmental effects. But anyway, if you have 44 grams of carbon dioxide, it will contain 12 grams of carbon and 32 grams of oxygen. And so the important numerical component of the law of definite proportion is what are called mass percents. This is typically how we, at least in this early stages of the course, how we're going to define the element composition in a compound. So if we have carbon dioxide, these are the numbers, and again, the two add up, the two elements, 12 grams, 32 grams, adds up to 44. That's a little bit of conservation of mass in some level. But the way that we sort of define things in a given compound is by what's called the mass percent. So mass percent is the mass of one of the elements in the compound, which I'll call element X, divided by the total mass of the compound. Now this ratio is called the mass ratio, but anytime you want to have a percentage, you have to multiply by 100. So make sure we keep that straight when you look at, ratios or fractions versus this will be more like the mass fraction, but this is multiplied by 100 to give a percent. So that ratio is called the mass fraction, and we multiply by 100 to give it as a percentage. And this is important because this is how we can define the composition of a substance. And so let's calculate it for carbon dioxide. If we want to find the mass percent of oxygen in carbon dioxide, we were told that the sample has 12 grams of oxygen. Sorry, 32 grams of oxygen, this carbon. So we have 32 grams of oxygen. The total mass of carbon dioxide is 44 grams. And then we multiply that by 100 to get it to a percent. That comes out to 73%. Okay? We can do the same thing for any other element. So this compound, carbon dioxide, only has 2 elements. So if we do the mass percent for carbon, we said that there was 12 grams of carbon, 44 grams total. I'm running out of room. Sorry about that. Let me try again. 12 grams over 44 grams, that's grams of carbon over the total mass of the compound, multiplied by 100 to get to a percent, that's 27%. And what we should notice also is that the 2 mass percents add up to be 100. So if you calculate the mass percent for every element in a compound, in this case there's only 2 of them, but some compounds have more than 2, add them up, they should total 100%, the total composition of that compound. And the reason this is important is because we can use these numbers to define the composition of carbon dioxide in any amount that we have or from anywhere that we would get it from. So this was, for 44 grams of carbon dioxide, but if we had calculated it for 44 tons of carbon dioxide or for just a little tiny bit of carbon dioxide, we would always get the same mass percents. Those mass percentages are an intrinsic property, meaning that they're constant no matter how much of that substance that you have. And so that's a useful way of classifying them. All right, so that's going to be the law of definite proportion. So let's do a couple of example numerical problems related to this. Okay, so the first one here is about pyrite, which you may have heard of as fool's gold, and that consists of iron and sulfur. So a 50-gram sample of pyrite contains 26.7 grams of sulfur. What is the mass percent of iron in pyrite? Now, one thing that I like to do when I'm approaching word problems, and you guys will see it over and over again in this class, and I encourage you to adopt similar habits, is start out by figuring out what is the question asking you for, because that's going to allow you to figure out what information you need to solve the question. Because sometimes the word problems can get kind of long, they have a lot of information. Usually we mostly give you necessary information, but sometimes there's even extra stuff in there. But if you go to usually the last sentence in the question to figure out what is it asking me, then you'll have an idea of what quantities you need to look for in the question or that you need to calculate yourself. So in this case, we're looking for mass percent of iron in pyrite. And as we just defined, mass percent of iron in this is going to be the mass of iron in the sample divided by the total mass of the compound pyrite. And then we have to multiply that by 100 to make it into a percent. So we know right at the beginning that these are the 2 numbers we need. We're looking for this, mass percent of iron. We need mass of iron and mass of pyrite. In many cases, one, or if you're lucky, both of those numbers are given directly to you in the problem. So mass of pyrite, we said we had 50 grams. So that number we already have. But if we look closely, the other number that we gave you in the problem is not the mass of iron, but the mass of sulfur. We need to find the mass of iron. Okay? So to sort of summarize that, the mass of pyrite is given to us. So in a lot of cases, some of your numbers will be given directly in the problem, so you don't have to do anything to find those. So that's given. But what we need is the mass of iron, which we don't have. But we can recognize that in a compound, because of conservation of mass, the sum of the 2 masses of the elements have to equal the mass of the compound. So the mass of iron plus the mass of sulfur has to equal that 50 grams, because that's the total amount of compound that we have. So then we can solve for that by a little bit of algebra, or just by difference, really, where we had 50 grams of pyrite. We're told in the problem that 26.7 grams of that is sulfur. And so the rest, by difference, must be the iron that's in there. So again, it wasn't given to us directly, but we can find it in this way. And so now we have the numbers that we need. The mass of iron is 23.3 grams. The total mass of pyrite is 50. We multiply by 100. and we get 46.6%. Okay? So that's going to be how we would calculate that, where we had to do just one extra step to get one of the two numbers that we needed. So that's a pretty classic math percent problem, and it's again it's the numerical concept that's most related to definite proportion. All right, now the other one we have is a little bit more advanced, and it's going to sort of show you another way of approaching that we can use this concept and approach this. So here we have the same substance, pyrite. We know that 50 grams contains 26.7 grams of sulfur, same given information as the last problem, but this time we're asking how many grams of sulfur are in a 1.235 gram sample of pyrite. So there's a couple ways we can set this up, but the way that I like to do it is what's called the factor label method. And so what that relies on is recognizing that mass ratios or mass percents can be used as conversion factors. All right, so if we know the mass of one element in a compound, we can build up a bunch of conversion factors that allow us to figure out the mass of another element in that compound, or the total mass of the compound. So basically all of these are related to each other and can be stated as ratios. All right, so that's what we're kind of the approach we're going to use here. So again, we go to the last sentence of the problem to figure out what we're looking for. We want to know how many grams of sulfur there are. So that's what we're looking for. And then in problems like this where we're using ratios of two quantities, in this case the ratio of an element, mass of an element to mass of a compound, then we look at what we're looking for. So, and what we're given. So we're given that we have a 1.235 gram sample of pyrite. And as we said, we can write a ratio of the mass of sulfur to the mass of pyrite, or mass of any other element to the mass of the compound. In this case, sulfur is what we need. So if we want to make sure that we set this up correctly, we want the mass of pyrite to cancel, to divide out, and we want to convert into the mass of sulfur. So this is called the factor label method. We just use units to tell us how to write this ratio. So we want grams of pyrite to cancel, and we want to convert into grams of sulfur because that's what we're looking for. So from the numbers in the problem, there's 26.7 grams of sulfur for every 50 grams of pyrite. So we can write that as a ratio. Grams of pyrite cancels out, and then doing this simple multiplication gets us into grams of sulfur. So it's going to be 0.659 grams. All right, so we'll see a lot more of that as we go through different types of problems in this course of using given quantities and ratios of given quantities in particular as conversion factors to go from mass of one substance into mass of another like we did here. So any questions on that before I move on? Yep.
For all kinds of word or math problems going forward, is there a specific decimal place that you want us to round to?
Yeah, so in terms of rounding answers in Blackboard, a lot of them are multiple choice, but there are a decent number of numerical problems where you have to type in the number. Usually we will specify how many decimal places to use, and you'll just need to follow that. If it doesn't specify it, or if you're in doubt, just follow the rules for significant figures, which you will review in the review chapter. So that's something we kind of expect you to already have a little bit of handle on. It's not that strictly enforced in this course, I have to say. We don't care about significant figures that much, but you need to be a little bit familiar with it. The reason we usually specify in Blackboard how many decimals to round to is because mainly we don't want people to put answers that are rounded too much and then get counted wrong because they're outside of the window that Blackboard accepts. So Blackboard will accept an answer that's within 1 or 2% of the correct one, depending on how we set it up. And if you round your answer too much, you might be outside of that just because of rounding. So we usually specify that to make sure that you don't round too much. So just follow the directions as closely as possible. In most cases, it will be specified. Anything else? Okay, so then the last mass law we want to cover. This is conceptually the most difficult, I would have to say. It's called the law of multiple proportions. So the key difference between the law of definite composition, which we just learned, or the law of definite proportions as it's sometimes called, and the law of multiple proportions, which is the third mass law, here we're dealing with two different compounds. So in the law of definite composition that we just covered, you're talking about a single compound, and the ratio of the mass ratio or mass percents of the elements that are in that compound all falls under the law of definite composition. For law of multiple proportions, we're talking about two different compounds, and the key is that they're two different compounds that are made up of the same elements. So a common example that you guys know is carbon dioxide, like we just talked about, or carbon monoxide. Both are compounds of carbon and oxygen, but different ratios. And so the law of multiple proportions sort of talks about the relationship between the composition of those two different compounds that have the same elements in them. So here's one way of stating it. It's a little bit complicated, but just bear with me for a minute. So if 1 gram of element A combines with element X to form two different compounds. So again, two different compounds, but they have the same two elements in them, just different ratios. So the masses of X that combine with A, so again, we're taking 1 gram of A and combining it with different amounts of element X to form two different compounds. But the masses of X that combine with that amount of A are simple whole number ratios of each other. For example, things like 2 to 1, 3 to 1, 3 to 2, etc. Very simple ratios, not like 100 to 73 or something like that. And so maybe a numerical example that's better. So just a random example. If we have our first compound has 1 gram of A with 0.5 grams of X. Let's say that's our first compound. Compound 2 could have a lot of different possibilities, but it's going to be some simple multiple of 0.5. So it could be, 1 gram of A with 1 gram of X, basically this times 2, or 1 gram of A with 1.5 grams, that times 3. So those two amounts, these amounts are going to be related to each other in a simple way. So if this is 0.5, this is going to be some simple multiple of 0.5. Double it, triple it, maybe multiply it by 3 over 2, but those are going to be closely related to each other. We're not going to do a lot of numerical problems with the law of multiple proportions. It's mainly going to be conceptual problems. And the dead giveaway for it is that when you're talking about the law of multiple proportions, you're always dealing with two different compounds made up of the same elements. So look for that. And if you see that situation presented to you, you should automatically think about the law of multiple proportions. We're not going to do too many things numerically with it. But just as another example of a sort of a demonstration of this isn't really a problem. This is just a numerical demonstration of this law. So we have two different compounds made up of iron and oxygen. So one of them you've certainly heard of, which is called rust. And there's this other one called ferrous oxide that clearly looks a lot different. It's magnetic. The magnetic properties are different. It's, color is different. Everything's different about it. So it's two different compounds, but they both only have iron and oxygen. And what you can see, though, is that the mass percents of iron and oxygen are different. So ferrous oxide, the black one, is about 78 to 22 iron to oxygen, whereas rust is about 70 to 30 iron to oxygen. So there's different ratios of the two elements in those compounds. So to demonstrate the law of multiple proportions, what we can do is look at the mass ratios of the two elements in each compound. So for ferrous oxide, we can do it in either way, either iron over oxygen or oxygen over iron. It doesn't matter. We'll get the same sort of outcome. But if we take the ratio of oxygen to iron in ferrous oxides, that's going to be this number, 22.27%, divided by 77.73. So the ratio of the two masses, or mass percents in those, that comes out to 0.2865. If we do the same thing for rust, we take the same ratio, oxygen over iron. Again, iron over oxygen would work. This is just a random demonstration. If you do the same ratio in rust, it's 30.06% for oxygen divided by 69.94, and that comes out to 0.4329. Now, those two numbers don't have an obvious relationship to each other unless you're really good at math in your head. But if we divide the two, if we take either way, we can divide either this one by that one or vice versa. But if we look at what the fractional relationship between those is, 0.4329 divided by 0.2865, that comes out to 1.5, which again can be stated as a very simple fraction of 3 over 2. So again, you're looking at the relationship between the compositions of two different compounds. You calculate the same mass ratio for each compound, and when you relate those two to each other, they're going to have a very simple whole number or small fraction relationship. 2 over 1, 3 over 1, 3 over 2 as we got here, and so on. So that's just a demonstration of law of multiple proportions. You're not going to be really doing too many numerical things with that on your own, but you need to recognize and understand the concept that's behind it and be able to recognize the situation, which again is always going to involve two different compounds, same elements. All right, so those are the three mass laws. So let's quickly review them and just give some nice snappy definitions of them. So we have law of conservation of mass. Mass is neither created nor destroyed during a chemical reaction, or matter can be stated that way too. So mass or matter is neither created nor destroyed in a chemical reaction. So the law of definite composition, or sometimes it's called the law of definite proportion. There's sort of two names for that one, so don't be confused by that, but it has the word definite in it either way. This is the one that deals with the composition of a single substance. So each individual chemical substance has a specific ratio of elements that make it up. And so that's one way then to define the composition of any chemical compound, any pure substance. So if you have an element, that element is going to be 100% composed of that single element. But if you have a compound, it's going to have two or more different elements, and you can define a mass proportion, a mass ratio or mass percent for each of those that defines the composition of that compound. And then law of multiple proportions is the complicated one. So I won't write it all out again, but basically if you have two compounds composed of the same elements, two different compounds, let me put different in there just to be clear. So two different compounds composed of the same elements, their compositions are related in a simple way. In other words, the ways that you can combine elements to make compounds is not really continuous. It's going to be sort of in a sort of stepwise way. If you have two elements combining to form one compound, the amount that would combine to form a different compound has to be some simple relation to that, not just a continuous function. All right, so that's going to be the three mass laws, and then what that leads us to is a theory that describes those mass laws. So as we said, the laws describe what happens, numerical observations or numerical definitions, and then the theory explains why those occur. And it's interesting and useful to think about the relationship between these two. So these are all covered under Dalton's atomic theory, and depending on how you break it up, it can have a few different parts to it. I broke it up into sort of 4 parts, and these are the things that Dalton's atomic theory says, and that kind of helps explain then all of those mass laws. Because the people that came up with the mass laws, they didn't really understand atoms and molecules at that level. But then Dalton's atomic theory said, well, if we have atoms making up all substances, we can explain all those laws that you guys just came up with. So Dalton's atomic theory, the first part of it is that substances are composed of tiny particles called atoms. So now surprisingly, the atomic theory involves the existence of atoms. Which cannot be decomposed further. So if you like analogies, atoms are basically the Legos of all matter. They're the things that we use to build up all forms of matter. And they cannot be broken down any further than at a single level. Another important part of this is that atoms cannot be converted into different atoms. And another way to say that is that elements cannot be interconverted. So you can't convert carbon into oxygen. You can't change carbon into oxygen. If you're talking about two different elements, they can't be converted into each other. Now this one is not 100% true. If you're at the surface of the sun or in a nuclear reactor, that happens all the time. One element converts into another. But in normal chemical reaction, the type that you would observe or study here on planet Earth, that just simply doesn't happen. It can't happen because the atoms cannot be broken down further. So if you have one element, you can't convert it or change it into a different element. The third part of this is that, how do we distinguish different elements from each other? So what makes carbon different from oxygen, different from sulfur, different from everything else, every other element, is the atoms that make them up are different from each other. So the atoms of a given element have the same mass and other properties as each other. So basically, if you have a sample of carbon, all of the carbon atoms in that are the same as each other, and they have the same mass and same properties. And those are all distinct from other elements. Now, as we will learn pretty soon, probably as early as next class, this one's also not 100% true. It is true that atoms that make up different elements have different properties, but sometimes they have different masses from each other, so that's the part that's a little bit wrong, but nonetheless it's still largely true and still informative. All right, and then finally the other part of this is the formation of chemical compounds. So chemical compounds form when atoms of two or more different elements combine in a specific ratio. Or another way to say this is that chemical reactions involve reorganization of atoms. So if you have a chemical reaction, the atoms and the reactants are combined in a certain way, and then when you do the chemical reactions, they're in the products combined in a different way. So you're talking about combinations of different elements to form compounds, and those compounds all have a specific ratio of elements. So these all, hopefully you can start to see the relationship between this and the mass laws that we just covered. And it's useful to think about that, and there will be some homework questions that ask you to think about that in more detail. Now, I'm probably not going to cover everything that I had planned today, but what I want to end with, at least get through this part, is some of the early discoveries that led to the determination of chemical formulas, which were done by two scientists, Guy Lussac and Avogadro. Avogadro we'll hear about later on as well. But the question now becomes, okay, we know that from the mass laws we can define the mass ratios of elements in a compound. So we talked about carbon dioxide already. 12 grams of carbon plus 32 grams of oxygen combine to make 44 grams of carbon dioxide, and we can define mass percents for each of those as well. But then the question is, well, how do we know how many atoms of carbon and how many atoms of oxygen are combining with each other to make carbon dioxide? If you've taken chemistry before, you should already know that carbon dioxide has the formula CO2. So that means one molecule of carbon dioxide has one carbon atom and two oxygen atoms. But how did we know that? How did we come up with that piece? The masses are relatively easy to measure, but how do we figure out then that the atoms combine in that specific 1-to-2 ratio in carbon dioxide? So this was came about from two different an observation and an interpretation, basically. So Gay-Lussac was doing chemical reactions on gases, and so what he found was that if you have gases at equal temperature and pressure, this is another topic that I think introduced probably earlier than we need to, but it is sort of related to some of this early stuff, so we throw it at you. This will make more sense later on in the course, but at equal temperature and pressure, gases combine in chemical reactions in fixed whole number ratios. So, for example, if you mix hydrogen and oxygen, that's burning hydrogen. That's a pretty violent reaction, so I won't do it for you. But if we take 2 volumes of hydrogen, 2 liters, 2 gallons, pick your favorite volume unit, and 2 volumes of hydrogen will always react with 1 volume of oxygen. They will always react in that specific ratio, and they will form 2 volumes of water vapor. So he carefully measured the volumes of gases that react with each other and the volumes of the products that form from them, and found that they always occur in very fixed and pretty simple ratios like this. Okay, so that's what Gay-Lussac found. And the way that Avogadro interpreted this, and we will learn later on about Avogadro's law that's related to this, but what he stated is that if you have gases at the same temperature and pressure...
Wouldn't that be 1 volume of water vapor?
2H10. Well, the reason for this is because hydrogen and oxygen exist as H2 and O2. So this is the part that's not going to make total sense right now. So if you balance that reaction, you have to do it that way. So don't worry about those details right now. That's for later in the course. But the point is that you have very simple ratios involved in all cases. And it's always the same ratio for any 2 gases that react with each other. It doesn't matter how you do that reaction. All right, so the Avogadro's interpretation of this was that if you're at the same temperature and pressure for gases, equal volumes of gas, and it doesn't matter which gas you're talking about, any gas, any different gas, have the same number of particles. And so what that means is that this chemical reaction up here at the macroscopic level, 2 volumes of hydrogen, let's say 2 liters of hydrogen plus 1 liter of oxygen makes 2 liters of water vapor. You can also interpret that at the microscopic level as we'll learn later on, this is the part that gets a little bit confusing, but hydrogen and oxygen are both made up of molecules, even though they're elements. So 2 molecules of hydrogen plus 1 molecule of oxygen those combine to make 2 molecules of water. So basically the ratios of the volumes equal the ratios of the atoms or molecules that combine depending on what that substance is made of. So hydrogen and oxygen are both H2 a molecule, O2 a molecule. That's something that we don't need to worry about too much right now. but it states that the macroscopic ratios that you can observe can also be then stated in the microscopic level in terms of the atoms or molecules that are involved. So that was Avogadro's interpretation of this, and so then by studying a lot of these gas phase chemical reactions, where you can easily measure the volume of the gases that react with each other and easily measure the volume of the product that forms, it allowed chemists to start building up what those chemical formulas are, because now we know the ratios of the two things that are combining, and that will give you then the ratio that they appear in that product. So at the microscopic level, here's sort of what it looks like with a couple of examples. So the one that we just gave you was hydrogen and oxygen. So as I said, hydrogen and oxygen exist as molecules. So you'd have two hydrogen atoms bonded together and to make molecules. So 2 volumes of hydrogen or 2 molecules of hydrogen, however you want to interpret that. And we said that combines with 1 volume of oxygen. So that means at the molecular level you have 1 molecule of oxygen. Put little symbols in there. 1 volume of oxygen, and those react to form 2 volumes of water, which is also made up of molecules. And the only way that this can balance out, the only way that the mass can be conserved, is if each water molecule has 2 hydrogens and 1 oxygen, which we probably all already know. All right, and so basically the ratio that they combine at the macroscopic level can be correlated to the ratio that they combine at the atomic or molecular level, and that allows us to then figure out the formulas of these. Because if 2 hydrogens react with 1 oxygen, that means, and they form 2 waters, they have to be this formula, H2O, for that to make sense. Again, the details of this, and there's not going to be really detailed problems of this. We just want you to understand kind of where this all comes from and how we got these formulas. Another example, so if we did hydrogen with chlorine, so we start with hydrogen again, but this time if we react it with chlorine, which also is a diatomic molecule, most gases are, as it turns out, for most gaseous elements, for reasons we'll get into later. But anyway, if you combine it with chlorine, what you would find in this case is that they react in a 1-to-1 ratio. So hydrogen and oxygen react 2-to-1, but hydrogen and chlorine react 1-to-1. So if you have 1 volume of hydrogen, that won't react with 2 volumes, or it will react with 1 volume of chlorine. But they will form 2 volumes of the product, hydrogen chloride. So since the volume of the product is double the volume of each of the reactants, that means we have to have 2 molecules formed as products to have double the volume. And so that means they have to be in a 1-to-1 ratio like this. Hydrogen and chlorine, 1 of each. So again, you can see that this time they react in a different ratio. Instead of 2-to-1, it's 1-to-1. And that leads us to formulate then that the product has a different formula. It's 1-to-1 instead of 2-to-1 as well in the molecule. So we don't need to know all the details of that, but as I said, it's important to recognize that, at least at the basic level, that doing these gas phase reactions allowed chemists to start figuring out what the chemical formulas of compounds were in terms of the number of each atoms that combine to make those compounds. And that allowed them to start thinking about that now at the more microscopic level as well. All right, I think we'll stop there today because I don't want to keep you over. So next time we'll continue on with this. If I don't get through the notes, I'll pick them up next time. I won't just leave them. So we'll be back with this at the beginning of next time and talk about now the structure of the atom, the different parts that make it up.